My name is McKim from Team Quarter, and we are here to present on our final design review for our structural integrity testing robot. So I'm going to start off by talking about the project definition. So over the past 2 quarters, we have been building up the skills and performing vast amount of research and design work to create a finalized capstone project that serves some sort of betterment for society. We began by each presenting on 5 ideas individually, forming groups, and brainstorming the type of project we want to explore. In the end, we settled on a project that took in some sort of frequency and performed a motion based on that input frequency. We came up with 3 primary ideas for the project, including a drum kit tuner, an automated baby crib, and a structural foundation testing robot. After performing extensive research on each project's necessity in their respective industries, along with how realistic each problem would be to design and simulate, we decided to pursue the structural integrity testing robot. So to begin designing our system, we had to ensure we could fully define our problem. We started with an initial problem formulation based off industry research in which the structural integrity of a building is tested with some sort of non-destructive testing method in which there are no automated alternatives. So a non-destructive testing method, just to be clear, is one that determines the sources of failure within a concrete without needing to break or penetrate the concrete. We also have a video here illustrating an impulse response test being performed on a highway. You can see the inefficiencies of this process with this video. So subsequent to the problem formulation, we further justified and explained the problem by studying the context, generality, design, algorithms, and solvability of the problem. These right here are listed to the left of the slide. After this, we performed a root cause analysis with the fishbone diagram to help identify the causes of the problem. Our specific solution will look to solve the problems mainly associated with the extensive manpower, so the manpower section, the methods of testing, the methods section, and the measurement section. After initially formulating the problem, we proceeded to put further time and effort into researching the non-destructive testing methods and how or why each method is used in the industry. The 2 primary forms of research involve the utilization of case studies or scientific studies performed in a university setting, along with industry interviews with companies who perform non-destructive testing methods. 2 specific ones that we happened to interview were Neodex and Smith Emery. Utilizing this research, we were able to settle on using the impulse response test as our primary non-destructive testing method for the robot. And we also decided to perform extensive background knowledge of this test and industry practices so that we could further specify our requirements. So to specify the requirements, we used a couple of different methods, with the first representing the objective tree method. This method primarily involves portraying the preliminary design objective as the root node of our tree, and this involves creating a reliable structural testing robot. We then proceed to define more nodes, in our case 4 more nodes, of the tree that encompass how we will achieve this one root objective. These nodes are defined as safety, effectiveness, functionality, and simplicity. This process is repeated from node to node until the requirements are sufficiently specified. Another method we use is called the quality function deployment method and involved using the information obtained from consumer interviews to list and assign weights of the requirements. By performing this process, we could compare our robotic solution against the competitors and obtain target parameters our robot needed to meet as listed in the bottom of the picture here. Finally, we can use these target parameters to create a block diagram that defines how we want the robotic system to operate in order to properly perform the impulse response test and offer our clients an initial understanding of the possible sources of failure in the concrete structure. The robot is defined as the overall system and is further divided into three subsections or blocks called movement, testing, and processing. These blocks are further divided into other blocks with arrows indicating how each of these blocks interact with one another. The process begins when the user inputs a floor plan, in which the robot will then plan the proper path to survey and test the structure. Once the floor plan is entered, the robot will use sensors to detect where it is in respect to the floor plan and move to the next location for testing. Once in the location, the robot will perform the impulse response test by placing a velocity transducer on the ground and striking the floor with an impactor. Finally, the frequency response detected by the transducer and the impact force created by the impactor are processed and stored within the robot to be provided to the user at the end of testing. After specifying our system, we started initial brainstorming of the different design options for the robot. We were able to summarize the different subsystems of the robot system and list design options for each subsystem. Once we were finished listing the different design options, we came up with three possible combinations of subsystems to incorporate into our final design. Using the requirements from the objective tree method and scoring the importance of each requirement, we could utilize the weighted objective method to compare the robots against one another and determine the best design of the three listed in the morphological chart. So this first slide illustrates the comparison between the first two robots. And as we can see, robot 1, in this case, scored better than robot 2. This next slide illustrates the comparison between robot 3 and robot 1, in which robot 3 scored slightly higher than robot 1. And then finally, we have a comparison between the final two robots, robot 2 and robot 3, in which the third robot possessed the highest score when compared to the other two again. And this will represent the initial design concept we will take in we will take into the next quarter, essentially. So again, here's a picture of the morphological chart for reference. We chose the third design option, which along each subsystem is outlined in red. And then finally, here's a picture of the final design of the robot. As you can see, a lot of the design decisions outlined in the morphological chart made their way into the final SOLIDWORKS model of the robot with a few distinct changes. The team will now go into how design decisions were made according to each subsystem, along with demonstrating the final simulations used to prove the success of our project.
So to begin with our design and engineering work, we're going to first talk about our navigation block. And our navigation block consists of the frame and drivetrain of the robot, as well as the path planning and path following algorithms that allows it to move across its space. So here you can see a screen capture of the drivetrain design. You can see the internal components that are within the yellow casing around our robot. This frame consists of C channels and angle beams, and we chose to use C channels because they achieve the necessary strength to support our internal components, but still remain lightweight. Additionally, C channels are a mass manufactured part that just need to be cut to size and welded together to achieve our frame design. And this makes them less expensive than the alternative of aluminum extrusions. The screen capture also allows you to see the internal arrangement of all the systems. You can see the striker, transducer, and actuating system that we'll go into a little bit later, but you can also see the electrical components that are powering the robot. As you can see, the batteries are distributed across the center axis evenly. This is to prevent the robot from tipping over during its motion. All of the electrical components also have custom housing so that they can be protected and easily mounted to the C channels. Additionally, part of our scope was to ensure that our frame would successfully fit through a standard doorway, and our frame design shown here successfully achieves that while still being able to fit all the electrical components and striking mechanisms easily. For our drivetrain, we used a four-wheel drive skid steering system. In order to decide upon a four-wheel drive system, we created two almost identical simulations in Webots. The first one using a four-wheel drive system where all four wheels were powered, and the second one using a two-wheel drive system where the front two wheels were powered, and evaluated the results. We tested both systems on their ability to do straight lines, gradual turns, spinning in place, and sharp turns. And the video shown here shows the four-wheel drive system successfully spinning in place when our two-wheel drive system failed to do so. This is the main reason we went with the four-wheel drive system. And rather than using 4 separate motors to achieve this motion, we chose motors on the front 2 tires and connected them to the rear tires with the chain system. This ensures that, one, it's less expensive because only 2 motors are required, but also that the wheels on each side will be rotating at the exact same velocity. With our drivetrain system and design complete, we needed to select adequate motors to power our wheels. First, we needed to determine the continuous torque and current requirements using basic physics applications on our robot. The derivations shown here allowed us to better understand the requirements for our drivetrain motors. And once this was complete, we found a motor that fulfilled all the necessary requirements based on the drive disposition plot you see here. The motor we chose is an 18-volt max and DC motor. These motors have graphite brushes, preloaded ball bearings, and a gearhead ratio of 156:1.
Okay, so in terms of path planning, we decided to restrict our scope so that each floor plan is made up of clusters where each cluster has one single width and one single height throughout the cluster. And because of this restriction, we were able to do path planning in each individual cluster and then just form a path from one cluster to the next. We also decided that the robot would only take 90-degree turns. So just another illustration of how the robot would move. It would go up through the cluster, then take a right, then go down through the cluster, and then take a left at that point. So in terms of the flow chart for this algorithm, we see that we start with the DXF, we go through some processing, and then we get to the part where the robot calculates whether it needs to drive straight or make a turn or stop to do testing. And it continues this process until it's finished with all the clusters in the floor plan. So we just also wanted to address some shortcomings. Due to time restrictions, we were not able to create our algorithm so that it would handle cases like this, where there are 2 vertical lines with the same X position. So other than these type of floor plans within our scope, we are able to handle all other floor plans.
So for the navigation algorithm, we have a couple of sensors that we implemented in order to do an accurate state estimation. And the sensor selection consists of 2 LW20 LiDARs, one that is on the front of the robot and one that is facing on the right of the robot. And we also used an IMU so that we could use the magnetometer component of this of the IMU. And these 3 sensors were combined, the sensor readings were combined in order to do our state estimator so that the robot could correct itself in its path in case it were to stray away from its path. And this is kind of a flowchart of the feedback system that we have. So there's 2 different locations used in the feedback system. One is where the robot actually is and where the robot thinks it is. So we use both of these locations to understand whether or not the robot needs to correct itself on its path. And then here you can see also a graph of the output values for the right LiDAR. And as you can see, there's plenty of noise involved. Therefore, the state estimator is very much needed. And then the illustration on the bottom is there to show that our robot takes sensor readings only when it's facing 90-degree angles. And that's just very important to mention. Again, for the path following algorithm, we used a pure pursuit controller. The pure pursuit controller is capable of being manipulated both for its linear velocity and also for its look ahead distance. So that illustration right there kind of demonstrates how the waypoints, the actual path, and the look ahead distance interact with each other. And then the GIFs under that show on the left what the robot would basically think it's doing if it were to never update itself using the state estimator. So as you can see, it strays away a lot from its ideal path it's kind of just going all over the place without the state estimator. And then on the right, you can see what happens when the robot is using the state estimator and updating its position or its where it thinks it is every 10 time steps. And you can clearly see how it can follow the path a lot more accurately. So here are some path following simulations. On the bottom left, you can see the robot doing a relatively simple path. And you can see in the MATLAB graph next to it how it updates the position where it thinks it is consistently, which helps it follow the path. And then on the bottom right, you can see in the GIF that the state estimator is actually not being used. Therefore, the robot is straying away significantly from its path and it's actually unable to correct itself. And finally, we also received some feedback that our robot should be able to detect unexpected obstacles. Therefore, here's a representation of what we implemented. Basically, what we did was add to the navigation algorithm a detection for unexpected obstacles in the floor plan. And when the robot does detect an unexpected obstacle, basically it just kind of sends a SOS message, as you can see in the animation right now, and it just the robot just stops. So here you can see some of the path following statistics. The first two graphs from left to right indicate the ideal X position versus true X position and the ideal Y position versus true Y position relative to their coordinates in the map. And as you can see, the orange line indicates the ideal position in that coordinate, and the blue line indicates the true position that the robot is using the sensors to acquire. And there is a slight deviation between the true X location and the ideal X location, but they are similar enough that we can say that our navigation algorithm was effective and the sensors are doing an effective job in estimating the state of the robot. And then on the far right, you can see the ideal strike spot versus the true strike spot. And there is a little bit more deviation here between the ideal position and the real position. However, since the strike radius is of 1 meter, and in that graph, the average deviation from the ideal versus real spot is about 20 centimeters. Again, since the strike radius is 1 meter, a 20 centimeter deviation, we think, will not have significant impact in the accuracy of the mobility readings.
The following slides will be discussing the analysis that went into our striker actuation. Initializing the design process of the actuation mechanism, the group performed research into the quantifiable metrics to determine what constituted a proper force delivery from the impact hammer. Two primary sources were utilized to help us identify the proper impact force and set up the parameters for our striker. The first source is a set of standards from the impulse response test on concrete plates released by ASTM International. The second extremely useful source involved a series of webinars released by Olson Engineering. Within these two sources, we were able to identify a force range of 13,000 to 20,000 newtons for our striker and an impact time of at most 3 milliseconds. While the act of performing a simple hammering motion is a trivial task for a human, it was quickly realized through our research that there are a myriad of ways of achieving a similar impact force through a robotic system. Each of these methods has their advantages and disadvantages. However, and as the striker is one of the most fundamental functions of our robotic system, each method needed to be analyzed rigorously in our selection. The most promising design schemes for achieving the specifications listed previously can be broken down into 3 methods: rotational hammering, linear actuation, and gravity-assisted freefall. The table in the slides serves as a tabulated comparison of these advantages and disadvantages. Comparing the pros and cons, the final design selection for the striker mechanism was the gravity-assisted freefall method. This method was appealing in nearly all aspects, combining the advantage of pure z-directional motion, hence no need for a stabilization mechanism, with the simplicity of the motion analysis of a free-falling object.
For our design, we found that we could achieve these design parameters by dropping a 2.7 kilogram weight from about 8 inches up to the ground. And the plots shown essentially show the force profiles for different parameters of concrete depth, coefficient of restitution of between our striker weight and the ground, and different elastic modulus of the concrete. And the design on the right is essentially our complete design of how the striker mechanism would function. We wanted to achieve a 3-second rise time in order to pick our weight back up. And using the motor configurations you see on the far right and the analytical equations that you see on the left and middle, we can operate our motor as shown in the diagram in the center, such that it will be performing within a reasonable range throughout the duration of picking up the weight.
The next portion of the striker was to develop a system for physically conducting the drop test. For this drop test, several methods were compared against one another. The driving specifications behind the final selection were the accommodation of the puck's mass and drop height as defined by our analytical model, and in addition to evaluation and the ease versus effectiveness of the potential design candidates. One of the most important aspects of the drop test design was to protect the motor used to raise the puck to its dropping position from any harm that could be dealt during the drop portion. In other words, a separate system that allows for motor disconnection needed to be implemented. There were 3 design options discussed when implementing this disengaging mechanism into our drop test, as outlined by options A through C, which you can see on the slides. Looking at both the advantages and disadvantages of each of the 3 options presented, it was eventually decided that the ideal drop test mechanism was that of option A. The primary reason for this decision was the disadvantages shared by both options B and C, namely the friction generated by the pulley interfering with the effectiveness of the drop. From the analytical calculations, a necessary drop height of 8 inches was determined to yield the ideal impact force profile. This calculation was done in the case of 0 friction, meaning that large frictional forces caused by the pulley could potentially lead to results that deviate drastically from our analytical models and thus be very difficult to simulate. Looking at these 3 options, there was no reason not to make the drop test as simple as possible, as a closer alignment with the analytical predictions will warrant a lower probability of failure. Similarly, option A guarantees that the mass is disconnected from the motor shafts 100% of the time, which may not be able to be said for either of the clutch solutions presented in options B and C. With this decision complete, the following section describes the selection of the electromagnet chosen for our application.
So given the design parameters we just mentioned, we chose to go with a 12-volt DC electromagnet, and it's capable of pulling 26 pounds, which far exceeds our capabilities. And in our nominal stage, our weight will be resting on the catcher, which we will describe in more detail later on. But this means that the electromagnet will only be operating for about 25% of the time. Furthermore, we have also incorporated a load cell that will be basically mounted inside of the weight, and it will be capable of measuring a 10,000 pound force, which again exceeds what we need for this project. And as you can see on the top right, we have a housing that we sort of developed that will hold the electromagnet in place, and 2 linear bearings that attach it to the same guide rail so that the weight will be sliding down. In order to avoid a second contact between the bottom of our weight and the floor, we needed to incorporate a catching mechanism. And we wanted to make this mechanism as simple as possible. And so what we found was that using a linear pull solenoid was the best way to do this. We essentially have our catching plate moving 1 inch in order to catch the bottom of the weight, and then 1 inch back to get out of the way. And this will only be in operation during the phase when the catching plate needs to be out of the way of the weight. And so that'll amount to about 15% of the time. And we also incorporated a photoelectric sensor that will basically tell our pull solenoid when it needs to retract and when it needs to extend. So in total, we needed to integrate all of these parts, and these 4 pictures here essentially depict how they all work in coalition. So once the weight has been picked up, as shown in the far left side, and we're ready for testing, the weight will drop and contact the concrete surface shown in the top right corner. And at this stage, the pull solenoid will be retracted. After the striker bounces off of the ground, we extend our pull solenoid back to its original position, and then the striker lands back on the catcher without contacting the ground and without hurting any of our motors. After this, the electromagnet returns back down and picks up the weight again. In order to verify our analytical results, we used an ANSYS simulation that essentially showed the same deformation and impact force qualities described above. And below is sort of a demo of how exactly we simulated this process.
So we also designed a striking algorithm so that the robot knows exactly which spots on the testing area it needs to strike in order to get the mobility readings. And as you can see on the graphs on the displayed, the striking locations are based on the striking radius and are calculated based on the height of the clusters in the testing area. So on the left graph, you can see that the striking radius is set to 3 meters. And on the right graph, the striking radius is set to 1 meter. And obviously, the striking radius with 1 meter, that graph has significantly more striking spots. Also, when the striking radius is set to 3 meters, there are some spaces that in between the striking areas that are not covered by the strike. So in a real life situation, the test engineer would have to see whether or not these spaces have a significant impact in the testing and tune the striking radius in order to acquire the data from that areas as well. And on the top, you can see a GIF of what the robot would look like when it is navigating a testing area, when it's advancing and then stopping to strike, and then advancing and stopping to strike again.
Okay, so now I'm going to talk a little bit about our second subsystem, the transducer. The first part for this subsystem was to choose what transducer we were going to use. It could be an audiovisual microphone or the geophone. We ended up going with the geophone because that's the industry standard for impulse response test. Everything else is just kind of new. And across the geophones, what we were looking for was a good frequency spectrum that was sensitive to low frequencies, and also to draw low power, so to avoid like needing external supplies or anything like that. We ended up going with the SM5 because across the other candidates, they all had different things. Some of them had really good low frequency response, but they needed external supply, or they were not high impedance. And then there were others that were not that good for low frequency. After choosing the transducer, we went and chose our simulation platform. We selected ANSYS because ANSYS has the tool called explicit dynamics that allow us to simulate impact in a surface. You can see here the picture of how the simulations look. Basically, we set up an environment where you can see the concrete slab with the puck and the transducer. And then we implemented the initial conditions of this. So the initial speed, the weight of the transducer to simulate our SOLIDWORKS designs. And then we did, velocity profile on the face of the transducer to simulate what the geophone would get in the voltage data. And we also did a stress analysis on the puck to get what force we were hitting with. By using these two things, we were able to calculate other things in the future. You can see here how the faces of the different shapes look, how the impact is performed after giving an initial condition, and how velocity in this looks for a crack and no crack. After using ANSYS for our simulation for the transducer and impact, we went and decided on our signal processing. As I mentioned, from ANSYS we get the time domain behavior of the impact. We used a Python script to apply fast Fourier transform to both the velocity and the force. And after doing that fast Fourier transform, we bring everything to frequency domain. And then from frequency domain, we divide the velocity over the force and get the mobility. This is a typical mobility spectrum that we would get. And then we just get the average of that, and we end up with one value, which is what we use for our final results, which we display in a heat map. So the heat map generation that we decided to go with was based on this reference. That's what is using the impulse response right now. And since we are working with simulations, we had to adapt some things. So we had to make a database first of different situations where cracks and cars can be. So you can see how we did a crack in the middle, crack in the edge, crack on the corner, and cracks. And then for each of these situations, we needed to have the different car positions. So a car in the middle, right above the crack, on the edge, on the corner, and all of that just to cover all the possible situations that the car can be inside the grid. After we did this, we had to discretize our original floor map. This floor map was discretized in all of these scenarios to kind of like distribute cracks along the floor map. And once the floor map was discretized, we generated our heat map. This is how the final heat map look. You can see there's these places in the middle of the heat map where you can see higher mobility values. These higher mobility values correspond to cracks, and those were assigned randomly and fact checked with the random generation. And actually, the cracks were here, so we ended up creating this heat map that has a very intuitive view that the user can easily see the heat map, see the cracks. And also, just for reference, you can see here how heat maps are generated right now. These are also based on average mobility. And you have high mobility values where the cracks are possible to happen. And in this case, because this is not a simulation, they have a more of like a smooth transitional here in the middle. But that we concluded that happened because of the beam situation that we had to simulate in this discretization for our initial conditions and the solid bounds. It created a beam structure, but still it's pretty visible where the high mobility spots are, and we are happy with the result.
In order to actually utilize the geophone sensor just described, we also needed to design a transducer lowering mechanism. This was accomplished via a 4-bar linkage. The 4-bar linkage, which can be seen on the image on the left, typically sits in the nominal position during navigation, in which case the geophone sits 1.5 inches above the ground. During a test, it is then lowered to a position such that the geophone makes flush contact with the ground, available to take a reading. This can be seen in the top images in the slide, where on the left side, the geophone sits in its nominal position, and on the right side, it sits in the position it would be in during a test. The mounting of this geophone linkage can also be seen in the bottom image to the rest of the assembly. So in order to control this transducer linkage, it was necessary to calculate the torque that would need to be exhibited, and this was accomplished by the calculations on the left. With this torque, we could then select a motor, which we chose from Maxon Group. The drive disposition is then shown here, and as you can see from the schematic, it sits very comfortably within the operating range. Here are the Maxon motors just described using a gearbox ratio of 326:1, as shown on the images on the right. Additionally, a contact sensor was added such that we could always verify when the geophone was in flush contact with the ground. Finally, the inside of the geophone housing was coated with a polymer-like material used to resemble skin, as we were told from industry professionals that in doing so, we would be able to match the shock that is typically associated with the human hand, for which the geophone sensors are designed, making the readings more accurate.
Okay, so our users also need a way to communicate with this robot, and the robot needs ways to communicate back with the user. So now we'll talk a little bit about our communication subsystem. So first, we started off by creating a UI flowchart, and you can see that the user starts with a DXF file, puts it into a remote computer that will calculate information related to path planning. The remote computer will then send this to the robot over wireless communication, and the robot will use its state estimator and motion controller to navigate throughout the floor plan and test at the relevant spots. The robot will then create a heat map and send it back to the remote computer for a couple final bits of processing. And then this heat map will then be displayed to the user as a graphical user interface. Since our path planning algorithm was based in Python and our robot controller for simulation was based in MATLAB, for the purposes of this project, we needed to create a way for these two programs to communicate. And so we decided to have the Python script write to an Excel sheet with all the relevant data about the path plan. And then the MATLAB script would then read all that data so that we can have our controller in MATLAB as well as our Webots simulation run correctly. And here you have an example of what that Excel sheet would look like. Okay, and so in order to give the robot the ability to interact with its environment and then communicate with the user, we had to add some more electronics and do a power analysis to ensure that it could last an entire days of work. So we started off by listing all the electronic components and their voltage and current requirements. And we then did a calculation based on the amount of hours it would be in service. We used 4 hours of continuous operation, because even though we want the robot to work for 8 hours, it will not be in continuous operation that whole time. So we think 4 hours of continuous operation will map over to 8 hours of regular operation. We ended up choosing this battery below 12.8 volts and 11 amps per hour. And we also created a circuit diagram where we connected all our electronic components to our microcontroller. And we chose the ESP32 as our microcontroller because of its built-in Wi-Fi capabilities, so that the remote computer could communicate with the robot, and the robot could also communicate with the remote computer.
After deciding our pipeline for data and all of that, we went on and created an intuitive user interface. One of the main objectives of our project is so that engineers can use it, and it will be something useful for the office engineer and reduce the workflow that they need to go over for testing. So we need to create an intuitive and useful application. This application that we created gives the user the possibility to upload a floor map. So the user has the floor map button. They do that. We apply all of our path following scripts to decide the waypoints and the places where we're going to hit, and it loads that into this viewer. This viewer tracks the position of the robot, as you can see here, and it helps the user where the robot. Other things that we added into the application was a percentage completion time and the timer, so that the user can see how much time has elapsed and how much time might be left. The user can also see the battery, which we calculated from our power formulas, and in the real implementation, it would be sent through the communication protocol. And then some temperature, again, this one was arbitrary, but this was just something that we felt the user of a robot that is working in a construction area with probably people around or something might need to know, just to make sure that everything's working. After the waypoints are done and the robot gets to the last part, you can see here how the completion bar is done, and it displays the heat map in the same spot. Again, this heat map shows the different places where cracks could be. These are the places where mobility is the highest. And yeah, this just allows the user to both monitor where the robot is going and observe the final results. In case they want to go more in depth, they have all the information in here.
In order to get a better idea of how our product fits into the market, we did a qualitative cost-benefit analysis of both the current system as well as our robot to make sure that it would be an economically viable options for the target companies. So looking at the current system costs, there's a high labor cost for outsourcing the testing, including hourly wage of the field engineers, the technicians, and the office engineers. And other direct costs include transportation, personnel to and from the site, and all processing of the equipment. Indirect costs for the current system include utility costs for processing data, which is relatively small. But the benefits of the system are that it does provide a heat map visualization of the possible voids in the concrete structure and signals the potential danger of deformations in the concrete. Essentially, our system has the same, if not more, direct benefits from the impulse response testing, but additionally, it avoids a lot of the high daily costs. And based on market research and interviews with members of the industry, we were able to come up with a number that the current system's daily cost is between $3,000 to $4,000 for equipment rental, outsourcing, labor payments, and more, while our system was priced at around $9,000 as an upfront cost, but with minimal daily costs.
So there's a couple of things that we would have liked to implement into our robot with more time. One of them being a more robust obstacle detection and avoidance system. So we think it would be very important for the robot to be able to maneuver around obstacles and then get back on its track. And that's something that we would have liked to add to the robot with more time. We also would have liked to implement a gyroscope into the sensor system and do sensor fusions so that the state estimator is more accurate. Also, we would have liked to add a brushing mechanism in front of the robot so that it could clear its path and make sure there was no debris or small obstacles that the sensors would not be able to detect. Another thing that would be nice would be an option for remote control, and this would kind of address any special cases that a test engineer would need to do, so that if the test engineer doesn't have an exact floor plan of the testing area, the engineer could simply just grab a remote control and then take the robot wherever it wants and get a mobility reading for wherever that spot is. And also something that we thought about was to implement multiple strikers, and we would have to do analysis on whether or not this actually would be more effective and if it would allow us to cover more area and more accurately. But yeah, that's something interesting that we were thinking about and we would have liked to analyze if given more time. So here's our robot in action. As you can see, the electromagnet lifts up the puck and then drops it when, and after the puck impacts the ground, the catcher is activated so that the puck doesn't hit the ground more than once. As you can see as well, the transducer is placed on the ground so that the geophone can take the vibration readings from the impact of the puck. And then the geophone is lifted so that it doesn't drag on the ground when the robot is advancing. On the right, you can see what the state estimator is outputting, which is basically a graph of the location where the robot thinks it is in the testing area. Finally, we'd like to mention some takeaways that we got from this experience. The many subsystems required to finalize this project cover a broad range of engineering challenges. We've learned what it takes to deliver an engineering solution from idea formulation all the way to end user satisfaction. Along with the technical challenges, the logistical challenge of delivering a project virtually taught our team how important it is to communicate effectively when making design decisions. Finally, we'd also like to thank our instructors, Peter, Yusuke, Professor Mehta, and Professor Rosen for all their guidance during this entire 2 quarters. And yes, thank you. This is Team Quarters presentation. We hope you liked it.